On February 4th, 2026, in San Jose, California, a company unveiled its pilot production line. It's called the Eagle Line, a test production facility by solid-state battery startup QuantumScape. As the news broke, it drew attention across the auto industry and among investors. Along with the recent debate around the Donut Lab announcement at CES 2026, more creators have started covering solid-state batteries, and the term is now being heard more often in the news as well. Today, we take a closer look at what solid-state batteries actually are, from the basics to where the technology is headed. When talking about solid-state batteries, various numbers often come up, like this. This means even after 1,000 charge and discharge cycles, about 95% of capacity remains. While it can charge in around 12 minutes, deliver high discharge output in about 6 minutes, and reach an exceptionally high energy density of 844 watt-hours per liter. Compared to LFP batteries, these figures are about 2 to 3 times higher. One of the most notable points is the much lower risk of thermal runaway. To better understand why solid-state batteries matter, often referred to as next-generation batteries, it helps to first look at how conventional lithium-ion batteries work. A battery consists of the cathode, anode, and electrolyte. During charging, lithium ions move from the cathode to the anode. During discharge, they move in the opposite direction, generating electricity. In other words, the key is how well lithium ions can move back and forth. The component that plays an important role here is the electrolyte. Most lithium-ion batteries used today rely on liquid electrolytes, where lithium salts are dissolved in organic solvents. Thanks to this, lithium ions can move relatively freely, almost like fish swimming in water. However, liquid electrolytes also have limitations. They can be vulnerable to heat or impact, and if the battery is damaged, there is a risk of leakage. There are also structural limits in increasing energy density, which means that to extend driving range, more batteries are needed, adding extra weight. This is where solid-state batteries come in. Instead of liquid, they use a solid electrolyte. This reduces the risk of leakage and offers the potential for higher safety. This is also why solid-state batteries are often said to lower the risk of thermal runaway. In addition, with more efficient structural design and next-generation materials, there is strong potential to increase energy density. In other words, they can store more energy in the same space. High C rates, such as 4C charging and 10C or 12C discharge, are also often mentioned as strengths. C rate refers to how quickly a battery can be charged or discharged. The higher the number, the more energy can be transferred in a shorter time. To achieve this, ions and electrons need to move quickly within the battery, and the structure needs to remain stable under high current. Solid-state batteries are being developed with this goal in mind. With all these advantages, why haven't they been used more widely yet? That's something we'll get into next. The reason solid-state batteries are difficult is not simply because the right materials haven't been found. Lithium ions need to move efficiently within the battery. Different materials need to stay in close contact, and everything needs to be manufacturable at scale. First, ionic conductivity. Lithium ions need to move well within a solid. Think of the difference between swimming in water and pushing through mud or gravel. If ions cannot move fast enough, charging slows down and power output drops, making it difficult for real-world use. Second, interfacial resistance. The electrolyte and electrodes need to stay in close contact. Liquid electrolytes can reach every corner of the electrode, but solids cannot. If the contact is not perfect, resistance builds up and performance declines. This issue becomes more noticeable as charging and discharging are repeated. Materials inside the battery expand and contract slightly, which can create small gaps at the interface. Even if everything starts well connected, contact can become unstable over time, similar to how a USB connector gradually becomes loose. Finally, cost and scalability. Solid-state batteries are not just about performance. They need to be produced at scale, with consistent quality, stability, and reasonable cost. So far, improving solid electrolyte performance has often required rare and expensive materials such as lanthanum or yttrium. In other words, improving performance raises costs, while lowering costs can compromise performance or manufacturability. Considering current LFP battery prices, this remains one of the most challenging aspects. Ultimately, the key challenge is not just making a high-performance battery, but turning it into one that can be produced affordably, reliably, and at scale. Efforts to solve these challenges are ongoing around the world. Earlier this year, researchers in Korea introduced an approach that focuses on changing the structure of the electrolyte instead of using expensive materials. What they focused on were divalent anions, common elements like oxygen and sulfur. The team introduced these into a zirconium-based electrolyte, which distorted the crystal structure. It's similar to inserting small stones between tightly stacked bricks, shifting the arrangement and creating gaps. These gaps then act as pathways for lithium ions to move through. As a result, ionic conductivity improved by 2 to 4 times, reaching around 1 millisiemens per centimeter, a level often discussed for commercialization, using only cost-effective materials. This study is meaningful in that it expands the possibility of designing solid-state batteries based on more practical supply chains. Industry efforts are also continuing. In early 2026, LG Chem developed a technology to uniformly control particle size in solid electrolytes, which is important for improving performance. Meanwhile, Solid Power has been researching sulfide-based solid electrolytes with high conductivity and strong process compatibility over a long period. In the EV sector, Toyota is targeting vehicles equipped with solid-state batteries around 2027 to 2028, while QuantumScape is moving through pilot production and validation using its own processes. Adoption will still take time, but progress is clearly moving forward step by step. While the previous video focused on EVs, solid-state batteries are drawing attention across a much wider range of applications. Smaller devices are likely to be among the first to adopt the technology. The technical barriers are relatively lower, and the market is more willing to accept higher product costs. The industry is already looking at potential applications in products like smartwatches and smart rings. Experience and manufacturing know-how built in these segments can make it easier to expand into larger applications. Next is robotics. For robots that operate in the same space as people and may fall or collide, safety is critical. At the same time, they need to store more energy within limited space, making energy density just as important. This makes robotics one of the areas where solid-state batteries show strong potential. For a deeper look, check out the video linked above. Drones and UAM, or urban air mobility, follow a similar pattern. In aviation, even a 1-gram reduction in weight can make a meaningful difference in flight time and efficiency. That's why solid-state batteries, with higher energy density and improved safety, are considered a very attractive option. In fact, LG Energy Solution and recent research on aviation electrification both highlight solid-state batteries as a promising next-generation technology for future mobility. In the end, solid-state batteries are not just about better performance. They could become a key technology that expands the possibilities of future markets, including EVs, robotics, drones, and wearables. Just as smartphones would have struggled to scale without Wi-Fi, there may be future markets that simply cannot open without solid-state batteries. Which product do you think will adopt them first? Share your thoughts in the comments. And if you want to keep up with battery technology, don't forget to subscribe and turn on notifications.